Hi, my name is Rodrigo Fernandez, and I'm going to present this project, Distributed Intelligent Video Surveillance for Early Armed Robbery Detection based on Deep Learning. This project was developed by Edwin Salcedo and I in collaboration with the Universidad Católica Boliviana San Pablo. This presentation will be divided into the following sections: introductions, objectives and methodology, system architecture, model training and performance, results, conclusion, and finally, we will have a question and answer session. Okay, introduction. First, I want to start my presentation with this question. Is it possible to detect armed robbery in terms of seconds using closed circuit television or CCTV? This question is the one that is behind the development of this project. What we're trying to solve is increasing crime rates in Latin America, particularly armed robberies. We need real-time crime detection system to help prevent these crimes from happening. In this presentation, I'll provide an overview of armed robbery detection using AI and IoT technologies. So, let's get started. Objectives and methodology. Our main objective is to develop a distributed IoT system for real-time armed robbery detection. This system will continuously monitor multiple locations and send notifications when a robbery is confirmed. Methodology. To achieve this goal, we followed a methodology that involved data collection from videos and public sources. Then we made some research about which technologies were the best for weapon detection. We decided then to use deep learning models for this task. After that, we read about YOLO and 3D CNN models and decided to use them for weapon detection and scene classification. Then we picked some frameworks to implement the cloud processing and the client-server communication. And finally, we compressed the models to deploy them on our edge device, which is a Jetson Nano. System architecture. Our system architecture consists of four main components, as you can see: end devices, a cloud server, a mobile application, and a database. The end devices are responsible for initial weapon detection. These are called nodes, are implemented on Jetson Nano devices and use YOLO BS5 for object BS B5S, sorry, for object detection. The data from these devices are sent to the cloud server for further processing with 3D CNN model for scene classification. Then the classification results are sent to another backend server that handles applica- a backend server that handles notifications to the mobile application, connection to our database, and communication with the frontend and mobile application. This diagram illustrates the flow of data from the edge devices to the cloud for processing. This way, we can confirm armed robberies with two different models. After the armed robbery is confirmed, the cloud server gets the user phone number from database and sends a message to the user and emergency contacts. This is done by using the WhatsApp WebJS API. Finally, the user receives a real-time notification on the WhatsApp mobile application. This system architecture allows for continuous monitoring of multiple locations and quick response to potential armed robberies. Model training and performance. Okay, first of all, weapon detection model. We train our weapon detection model on a database of over 60 16,000 images, combining samples from SOHA's weapon detection and COCO datasets. We use YOLO B5S with TensorRT optimization for real-time inference. The model achieved a mean average precision of 0.87, demonstrating its effectiveness in detecting weapons. We apply preprocessing techniques such as brightness and contrast calibration, background removal to improve detection accuracy. Additionally, we implemented a momentum algorithm to calculate weapon detection confidence. In the other hand, with armed robbery classification model, for the armed robbery classification model, we trained a 3D CNN on a dataset of over 1,000 videos collected from UCF crime dataset and social media sources. The model achieved an accuracy of 0.88, demonstrating its ability to classify robbery scenes accurately. We applied preprocessing techniques such as normalization, grayscale conversion, and data augmentation to enhance the model performance. These results show the effectiveness of our approach in detecting and classifying armed robberies in real time. Results. Before showing the results, I want to address the challenges we face with knife detections. As you can see, the left confusion matrix illustrates the comparison between the ground truth and the predictions made by the YOLO B5S models with guns, knives, and backgrounds. We observed a higher number of mistakes in detecting knives compared to guns. This is mainly due to the reflections and varying light sources that affect the detection of knives. This is an area for future improvement, but for now, we focused on guns for the best results, and also because they are more common in armed robberies. Because of that, in the right side, we have the confusion matrix of guns and backgrounds. The results are very good, with a high number of true positives and true negatives. Here in weapon detection results in this slide, you can see two tables, one with different versions of YOLO models and their performance metrics, and the other with results obtained by combining additional steps in the inference pipeline implemented in the end device. First, in the left side, the table that compares the performance of different YOLO versions, we can see that the results of every model are pretty similar. So we based our selection on the speed and deployment evaluations performed in previous study. The result, YOLO V5 was the best model for our system. Also, inside YOLO V5, we picked the specific version, YOLO V5S. This version was the one that gave us best results. On the right side, we have the results obtained by combining additional steps in the inference pipeline implemented in the end device. The different options we tried were brightness and contrast calibrations, BNC, background removal, BR, TensorRT optimization, TRT, and the momentum algorithm, M. The best results were obtained when? Of course, the third time, when we combined all these steps except for converting the frames to black and white. As a result, we achieved an accuracy of 0.75, an F1 score of 0.74, and an AUC of 0.74. This shows the importance of these additional steps in improving the performance of the weapon detection model. Then our robbery classification results. Now let's move on the results of this model. After getting the results of weapon detection model, we send the following 30 frames after the detection to the cloud to evaluate the 3D CNN model. The results are shown in this table. The best results were obtained when sending 15 frames per second during 2 seconds to the cloud. In other words, saving one frame and skipping one frame. This way, we achieved an accuracy of 0.88, an F1 score of 0.87, and an AUC of 0.88. This shows the effectiveness of the 3D CNN model in classifying armed robberies scene accurately. Finally, the conclusion. We have developed a distributed IoT system for real-time armed robbery detection that combines edge computing and cloud processing. This system has demonstrated the ability to monitor multiple locations simultaneously and confirm armed robberies efficiently. By integrating deep learning models for weapon detection and scene classification, we have achieved promising results in detecting and classifying armed robberies in real time. This technology has the potential to enhance public safety by providing real-time alerts and notifications to authorities and individuals. Future improvements could focus on enhancing knife detection, optimizing the system performance, and exploring potential applications in other contexts such as traffic monitoring, crowd control, and even emergency response system. Thank you for your attention. As long as this is a recording presentation, I will be available to answer any question in a moment. Please feel free to ask any questions you you may have about the project, and I'll surely be happy to answer them. Thank you so much.